Link. Okay, you are on.
Thank you. And thank you for the invitation. Can you see the slides?
Yes.
Okay. So my video froze a bit, but I don't know. I guess it's okay on your side.
Still first page.
Right. Okay. Fair enough. So thank you for the invitation and thanks for calling in. And today I would like to speak about the interplay of the CernVM file system and containers. Let's start with a brief overview of the current deployment of CVM-FS. This is the worldwide map that shows both Stratum 0 and Stratum 1 services, so active services, content providers, and the WLCG register script proxies, which are more or less the main caching infrastructure and sits on the edges of the grid sites. And of course, what we want to do with CVM-FS is to make a well-functioning global delivery of experiment software stacks, but then also of the platforms that are underneath the software stacks, which means containers today, and certain limited forms of data. For high energy physics, this is in particular as a conditions data, so the state of the detectors at the time of data taking. And in numbers, we have more than 1 billion files under management. So we are aware of about 10 large Stratum 1s in Europe, America, and Asia, and something like 400 site caches. One thing that I think has been a very nice development over the course of the last year or so, and with preparation from many years before, the CERN Stratum 1 is now fully hosted on Ceph S3, not anymore on a conventional file system. So a quick zoom into the EGI land. Of course, there's not only CERN being a content provider, but most notably RAL for EGI, but also IN2P3 and NICAF and DESI, and perhaps others that I'm not aware of. So what is the content that we actually serve on CVM-FS? Well, it's the production software like /cvmfs/atlas.cern.ch, but then also the integration builds, the nightly builds that correspond to the production software, for instance, LHCb dev for the LHCb collaboration. That is actually the most challenging workload for CVM-FS because there's massive churn. So nightlies, they get published every night and they have to be cleaned up from the week before, and there's also strict requirements on propagation. So that is a focus of development, good support of the nightly build repositories. Then unpacked container images like /cvmfs/unpacked.cern.ch, and this will be a focus of this talk, and it's also a focus of current developments. And auxiliary data sets, for instance, the Alice conditions data, but also a few others. I think that, for instance, there are some genomics data in CVM-FS, and so there are certain data sets, like on a smaller scale, where it works well. Right, so let's have a look at the repositories that distribute containers, and I would call it sort of a grids container hub. There are in particular 2 repositories to be mentioned here. There's a CVM-FS unpacked.cern.ch and CVM-FS singularity.opensciencegrid.org. Both host by now more than 500 images, different images. Both provide more than 2 terabytes of images, and in a decent number of files. And also, I mean, if you look at what sort of images, it's really a wide variety. There are base operating systems, experiment software stacks, but then also explorative tools. For instance, let's say latest version of TensorFlow and others. Some user analysis, and also special purpose containers now with the efforts to fight COVID. There's the folding at home container also available from CVM-FS. And it's actually quite nice and simple to use that. With Singularity, it can be directly started, as you can see in the command on the lower side, lower half of the slide, Singularity exec, and then you specify which container you want to run, and you see that the file system structure here resembles the resembles the structure of the registry. So there's a directory for which registry you want to get the image from. In this case, like the Docker hub, but there's also gitlab.cern.ch available, and then the specification of the image. And okay, in this case, I ran it on LX Plus at CERN, but this can run equally well on the grid on a CC7 node, and I start my Debian environment. Right, so I would like to speak a little bit about containers and HAB or the grid in general. What actually do we want from containers? I think that we want from containers 4 fundamental properties. We want isolation. So if we have 2 applications on the same host, application X should not somehow make application Y crash, for instance, because it uses all the memory. We want platform independence, so applications that can run on any Linux, and they simply bring all their dependencies with them. Then what at least the industry standard container ecosystem also sort of promises as a property is the distribution, the easy distribution of software. So you go to one hub like Docker Hub and you find the software you need. And then once all of this has been sort of standardized, actually higher level services can be put on top of it, orchestration. And here the de facto standard is Kubernetes becoming the de facto standard, so to schedule distributed jobs on multiple nodes. Now this is, all of that is not completely new to the grid and to our energy physics. And we have thought somehow about the problems and came up with sort of traditional solutions like a batch scheduler, distribution from CVM-FS, something like HAB-OS libs to give some sort of platform independence. And so in the context of this talk, I think what we are actually aiming for, what we want to have, is all the nice properties from the industry standard tools, isolation, orchestration, and also the standard sort of surface of containers. But we want to connect it with the flexibility and the efficiency of CVM-FS-based software distribution. And so let's have a closer look at this particular point of the distribution. I would like to start with some file system gymnastics to introduce a bit the words. So let's start with the image, the container image, and the container image defining the content, defining actually the software stack that runs. And that can come in sort of 2 forms. It can come as a tarball packed, or you can then untar it and see it as a part of your directory tree. And what happens when you start the container, you have somewhere in your file system on the host, let's say in var lib containers, you have a directory with the root file system of the image that you want to start. And if you look at the distribution point of view, the container runtimes typically distribute these tarballs on the left-hand side, and then on the local node, they transform it into the directory tree on the right-hand side. If you think about CVM-FS, we get the right-hand side, the directory tree, in the form of a network file system. Now, this can be a bit refined. We have layers in the container runtime, so we can partition our image into several layers, let's say a base layer in blue and a layer in red that gives us the actual application software on top. And these layers are, I think they have their biggest advantage for composing the image when it's created. It's not so much for the distribution efficiency, but it's really like when I create an image, I do not want to think about what sort of Linux do I have to put in the image, but I start with something stock, like let's start with an Ubuntu image or CentOS image. that is where the layers are really super useful and and help productivity. So now we have these two directories, but we have not yet the root file system that we can run a container from. So the next point is the overlay file system. Overlay file system allows us to take two directories and sort of merge them virtually together to get something like the one on the right side, which we then can actually chroot into and run. Right, and they do usually the overlay file system does one more trick. It puts an empty layer on top of everything so that the result is writable. So the right side is actually a writable root directory. And the last point, the underlay, is a means to get from a read-only root file system to a read-write root file system. That's particularly interesting for CVM-FS. Let's say we have our root file system somewhere in CVM-FS on the left side. It's read-only, so we can start a container, but it's not that useful usually. But what we can do, we can create a skeleton of the root file system and then bind mount all the parts that are fine to be read-only and create empty directories in those places where we actually want to write to. There's a technology which is, for instance, part of Singularity, the underlay, creating an underlay. Now a little bit on distribution efficiency. We looked approximately half a year ago into unpack.cern.ch and singularity.cern.ch to see what's the anatomy of the images, how do they look. And so one of the things we looked at was the image size. We find a large spread in image sizes from a few hundred megabytes to tens of gigabytes, with a mean at a couple of gigabytes. So they are not exactly small, at least at the moment, and they are. It's if you think of a big worker node, you have a worker node with 64, 128 cores. You can imagine it's quite easy to overflow the local cache with images of many gigabytes in size. And we looked a bit at the deduplication, and we compared here deduplication of layers versus deduplication of files. So this you see the first bar is like just the sum of all the images, size and number of files. Then the layers bar is all the unique layers, and on the right side you see like all the sum up of all the unique files. And well, perhaps a bit surprisingly, it turns out that the sharing of the layers, what you can gain in terms of deduplication, is not all that big. And definitely what's the case is that the file granularity gives the actual benefit of deduplication. And if you look into runtime behavior, it's not only the fact that we have better deduplication, but also with a file-by-file based distribution, we have to load much less into the worker nodes caches. We have to load much less from the network because we load exactly those files from the layers that are actually needed, and that's usually just a few percent of the files available in an image. So we have a by factors better distribution efficiency from CVM-FS, and that is also that means we can actually effectively and easily run images at scale in the grid, for instance. So what can we do to make container integration with CVM-FS easy? What's the current state? I would like to distinguish two cases. On the left-hand side, case one is, let's say we have a container and we want to make /CVM-FS available to that container. And so if CVM-FS is available on the host, then it's very simple. We can start the container and bind mount CVM-FS inside. But we have also some approaches for more opportunistic cases where CVM-FS is not necessarily available on the host. And then on the right-hand side, here the question is, can we start the container image itself from CVM-FS. And so that requires two things. First, it requires the container image that probably is initially in the form of a Docker container, let's say on Docker Hub. It requires that image to be converted and to be exploded, the root file system needs to be published to CVM-FS. There's a service for that. And the second point is that we have to teach the container runtime to get the image from CVM-FS instead of downloading a tarball. So I would like to start with the left-hand side. What can we do to provide CVM-FS in an existing container? Well, if CVM-FS is available on the host, that's the simple case. We can run docker run, and then with -v, we bind mount from the host into the guest. The important bit here is that we bind mount CVM-FS in shared mode, so that, because usually /CVM-FS is auto-FS mounted, and what we want is that if we inside the container, we trigger mounting a new repository, that this is actually propagated to outside the container, and let's say /CVM-FS/cms.cern.ch gets actually mounted. So that is what we can do with a shared flag. And well, the same we can do with Singularity. We don't have to specify anything special. We use -B/CVM-FS, and that's it. Now, if we do not have CVM-FS on the host, there's a utility called CVM-FS exec. And CVM-FS exec knows a number of different tricks to make CVM-FS available in a confined subshell. And one of its tricks is actually using container technology itself. So the technical foundations are in the lower half, but essentially what happens is that CVM-FS exec starts sort of half a container, enough of a container to mount CVM-FS inside that confined area, even though it's not available on the host. And what's required for that is a relatively modern Linux to make this work. It relies on user namespaces and unprivileged fuse mounts, and that should be fine as of EL 7.8 and EL 8. Then a new way to get the CVM-FS client. We are just finishing. This is for the 2.8 release. This is the CVM-FS service container. So what this is a container that contains a CVM-FS client, a minimal container with a CVM-FS client. And this container can be started and used to provide /CVM-FS to the host. And it can be started in such a way that it leaks the /CVM-FS area that is mounted inside the container to the outside, to the host. And that could be a practical way to get CVM-FS up and running. For instance, on platforms where we do not provide packages for. For conventional Linuxes, we have CVM-FS client packages, but if you run, let's say, a container-only OS, something like Atomic, then the only way to get something there is a container. And you can see on the lower half how this would work. Docker run -d, so we start the container in daemon mode. We can set a few CVM-FS environment variables. Currently, we have to give it some permissions, the sysadmin and the access to dev fuse, but I would hope that in the future, mounting fuse file systems becomes more of a standard option of container runtime. So these extra capabilities should at some point go away. Again, we bind the volume in a shared mode and start the container. And the second line, ls/CVM-FS, is executed on the host. So the first line starts the container in daemon mode. The second line runs on the host, but it uses the CVM-FS that is provided from inside this daemonized container. And that is the fundamental building block. That container is the building block also of a possible Kubernetes deployment. So if you have a Kubernetes cluster and you want to make /CVM-FS available to your pods, you can actually use the service container to deploy a daemon set. So to have one of those service container running on every node that gives then access to CVM-FS to all the pods. And I've linked a sample deployment in the slides. What's missing is to make this a Helm chart. I hope that we get to this sometime next year. And then for perhaps more of a special case, there's integration with the Singularity pre-mount or user mount feature. And this is probably something that is mostly targeted for HPCs. So the idea here is that we assume that we do not have the permission to mount CVM-FS on compute nodes, but we assume that Singularity is available, and the HPC side sort of trusts Singularity to do the mount for us. And we can ask Singularity to do the CVM-FS for us with the Singularity -- fuse mount option. This requires a relatively new fuse, fuse 3, and in particular it requires that the container that we start has CVM-FS already inside, has it installed. So it requires a little bit of preparation. And what then happens is, so we can see this in the example script, Singularity with this fuse mount option would take care of the privileged parts of the mounting and then hand over that privileged part to the CVM-FS fuse module inside inside the container. And that is a special container that I use for this example. It has been prepared by Dave Dijkstra, CVM-FS-Fuse 3, and with this container, this can be tried out. Now, coming to the second part of containers in CVM-FS, what can we do to start containers from CVM-FS? Well, the first step is, as I said, the conversion. So let's say we have a container that we want to make available. It is available in a Docker registry, for instance, at Docker Hub, or perhaps at GitLab or at another registry. What the way this works at the moment is that CVM-FS server has a special service, a container conversion service. It's called JAK, that can run on the publisher node. So this service runs on the writer side of CVM-FS unpack.cern.ch, and it looks at the wish list. So the central point of image conversion is the wish list that you can see on the left-hand side that specifies which container images do we want to make available in /unpack.cern.ch. And this wish list is passed periodically, and the newest versions of those containers are all the time made available. And you see you can also use some wildcards, for instance, get all the versions of CentOS to unpack.cern.ch. Now, if you look at the right-hand side, how do the images end up in unpack.cern.ch? They end up in two forms: as a flat exploded or unpacked root file system. This is the first line, like Fedora latest, and that is the entry point that you can use with Singularity. But we also convert the individual layers and explode and unpack the individual layers. And that can be used to then run the container of CVM-FS with layer-based container runtime, such as Containerd, and then Kubernetes to the extent that it uses Containerd and Podman and others. There's an ongoing work to provide a tighter registry integration, to provide an alternative way to get images into CVM-FS, simply triggered by Docker push, so that you do not need to explicitly list images on the wish list. And this is expected for 2021. Right, so then with container runtimes that can run directly from a root file system, it's very easy. That's the same example from the beginning, Singularity exec, but it also works with other runtimes. For instance, with Docker, there's a graph driver plugin. For Containerd, there's something which it's called a remote snapshotter, also sort of a form of a plugin. And for Podman, we have a pull request pending that produces the necessary metadata in unpack.cern.ch so that Podman can use it directly as an image store. We think actually that the graph driver for Docker, or we hope that it in the future won't be necessary anymore once Docker moves to a newer version of Containerd. So as of Containerd 1.4, there's this facility of a remote snapshotter. The remote snapshotter provides the capability to start layers that are expanded in a file system, to start layers, let's say, from CVM-FS or other network file systems. And and in this way, you have a direct integration between CVM-FS and Containerd to start your container. So here's an example where we really had a large-scale deployment. This is folding at home container which ran on the grid in the effort to fight COVID-19. It ran off CVM-FS, and you can see if you look at this team statistics, CERN and LHC computing is at team rank 17, and that's really not that bad. So it's just next to illustrious names such as Microsoft, NVIDIA, and others. And so that means we have really provided quite some work units to this project. It also means the container has been run in many places. So the last point I want to mention is the ephemeral publish container. Now this switches context completely from the client side to the server side. And we have, in particular, we have a point, so where the point of publish, which is currently a single point, a single machine usually to write new content into CVM-FS. And of course, the question for everyone who publishes content in CVM-FS is, how do I build my software and then transfer it to this publisher node? And a particular problem can be that you want to, on the build node, you want to install your software in /CVM-FS something, but your /CVM-FS something is a read-only directory. You cannot do make install into this destination path. Now, what we will be able to provide with a 2.8 release is a CVM-FS server enter command. And the idea is that on any node that has the client mounted read-only, we can use all the container tricks to provide a confined, ephemeral subshell that has writable access to /CVM-FS. So it would open, principally it would open a container. It would then use fuse overlay FS to make the read-only the read-only /CVM-FS writable. It would store the state somewhere in a temporary directory, and this should work unprivileged on any modern Linux, meaning any Linux that has username spaces and unprivileged accounts available. If you want to try it out, there's a pull request open. We are still finishing this for the 2.8 winter release, and you can see on the lower half how this would work. So let's say you have a machine where you have hsf.cvmfs.io mounted read-only. You would call this command and open a subshell that gives you write access, but like a local ephemeral write access to this to /CVM-FS HSF. Then you can make some changes and look at the changes, for instance, tar them up and send them to the publisher node. And once you go back to read-only mode, the state is restored, and like whatever you have written is discarded together with a scratch space. Right, so that brings me to my summary. First, perhaps an announcement. I would like to announce two upcoming events: the EGI clinic on HT Condor and CVM-FS on 3rd of November. And secondly, the CernVM workshop 2021. It was originally planned to take place at NICEF, 1st to 3rd of February. Now we will make this largely a virtual event, 3 afternoon sessions. There will be a meeting room at NICEF for local participants. And we will, of course, discuss containers and CVM-FS, but also many more topics. Now, as a summary, I thought I lay out a bit what I could imagine being a successful container strategy for the grid. I think we should exploit isolation and orchestration capabilities from the standard tools, Singularity, Podman, Kubernetes, and so on. At the same time, we should exploit the distribution efficiency from CVM-FS. And there's continuous effort from the CVM-FS team to provide good integration with container runtimes. And what I could imagine how the software stacks perhaps already look like, and even more so perhaps in the future, is sort of two possible ways how the containers would look like on the grid. The first one, let's say for our production workflows, simulation, reconstruction, well understood analysis cases, I would imagine that we have a minimal container that provides a compatibility layer, that provides a standard platform on which other software can run. So this would essentially be a glibc plus epsilon plus a little bit, maybe only a glibc. And then on top of it, so this container could start either from CVM-FS or from a regular registry, and then we would bind mount CVM-FS inside this container and provide all the application, all the app universe that CVM-FS has. And that means we can combine from different CVM-FS repositories, we can use the data repositories and so on. And so I think that for those cases, it would actually be unnecessary and an unnecessary constraint to think about the cutting of containers up front. However, I think there are other cases where we already have full containers that are just fine in itself. For instance, let's say explorative workflows, where I have a certain machine learning tool packaged and I want to test it on some large scale. Or I have perhaps the COVID, the folding at home container. So here, of course, I do not want to go through the hassle to put this somehow on CVM-FS first, but I want to take the entire container as it is. And in this case, I think this makes sense to run unmodified and from unpacked.cern.ch, so that we do not have to rip out the application software from the container. And with this, I thank you for your for listening, and I'm open to questions.
Thank you very much, Jakob, for your. Is someone's microphone open? Anyway, thank you very much. So I will stop recording now.